Climate change. It sure is a big wicked problem, and when trying to understand the bigger picture, it can be hard to know where to start. So, whether you're in need of a place to start, or info to reinforce what you already believe, or you want to try and debunk the whole thing, you're going to want to answer the question, is climate change definitely human-caused? Because if our emissions aren't causing it, there's no point in decarbonising. The argument for humans causing climate change is supported by two pillars. First, the principles, which state that emitting greenhouse gases inherently leads to warming and a changing climate. And second, the evidence, which is all the data we have to determine how big our effect actually is on the planet. So let's dive in. The year is 1861, and a professor named John Tyndall has just published a research paper explaining the findings of his latest experiment. What he'd found was something interesting in the way certain gases behaved under heat radiation. He noticed after hundreds of repeated trials that whenever he directed a source of heat radiation through a long tube filled with water vapor, the amount of heat detectable on the other end was lower than if the tube was just to be filled with dry air. The only explanation for this was that the water molecules in the air were somehow absorbing this heat before it reached the end of the tube. He also repeated the same experiments with a number of other gases, including carbon dioxide, and found higher amounts of heat being absorbed by those. 1.5 centuries of scientific experimentation later, and the science behind it is now very well known. The reason these molecules absorb heat radiation has something to do with their molecular structure. These molecules, such as water vapor or carbon dioxide, usually float around in a certain stable shape, which balances out tiny positive and negative charges on each of these atoms. However, radiation at a certain special wavelength can knock these atoms out of balance, and this tiny imbalance of charges is what's called a temporary dipole moment. The dipole moment only exists for a very short time, as the radiation is absorbed by the molecule to change shape, but then it's spat back out, and the molecule returns to its normal state. But this happens over and over again, making the molecules vibrate and the radiation able to get stuck bouncing around different molecules. This vibration effect is what makes the temperature of the gas rise, as well as the redirected radiation being free to hit other surfaces to increase the temperature of those as well. And what we find is that the wavelength most common in sunlight isn't long enough for CO2 to absorb, so a large portion of sunlight makes its way to the Earth's surface. However, when the Earth's heat causes it to emit radiation back out, it does so at a much longer wavelength, which gases like carbon dioxide and methane can absorb. So heat begins to get trapped in the atmosphere and redirected back towards the surface, which means more heat comes off the surface, etc., creating a powerful cycle. And we know this cycle can be really powerful because 20% of what stopped Earth from being a completely frozen wasteland for most of human occupation has only been 280 molecules of carbon dioxide for every million molecules in the atmosphere. The rest is due to water vapor and clouds, which are only present for a very short time, but are also known to increase when the temperature increases. So after Tyndall's first experiments, the name of the greenhouse effect would soon come to be. And with enough repeated experiments, it's reached the level of unquestionable scientific fact. There's also no question about the amount of greenhouse gases that humans are emitting. At the time of Tyndall, humans were pumping out 348 million tons of carbon dioxide into the atmosphere every year. Nowadays, we pump out 36 billion tons, or the volume equivalent of almost one Olympic swimming pool per person alive. And then there's other types of greenhouse gases, which we're emitting as well. Now, that sounds like a lot, but how are we supposed to know if that has any impact on a system as big as the Earth? That's where we need evidence. With these principles, we have a solid argument to say that we're definitely having some warming effect, but we need evidence to know if that effect is anywhere between negligible and planet changing. So first up, it'd be handy to put our carbon dioxide production into Earth's perspective. So we need to know what CO2 levels on Earth are usually like and if we're changing them. For this, we can look to the ice cores in Antarctica and Greenland. When snow falls in a region continuously for a very long time, layers of snow and air slowly get compacted. Once they're compacted for long enough and under enough layers, they start to form ice sheets with little air bubbles, which scientists can now dig down to find. Taking those little air bubbles, we can get a snapshot into what the atmosphere was like at that time, and we can use carbon dating to know how old that air is. We can also take the water molecules from the ice to see how many have more neutrons than usual, because we know temperature affects how many of them get evaporated to make snow. We can also take ancient temperature measurements from a few other sources around the world, but ice cores are our main go-to for carbon dioxide levels. Anyway, using this technique, the furthest we've managed to look back is 800,000 years, which tells a story like this. Every 100,000 years or so, the Earth goes through a cycle of ups and downs in carbon dioxide, which coincide with the Earth's routine ice ages. Let's look specifically into the lowest point in the most recent ice age, around 20,000 years ago, when studies have shown giant portions of the northern hemisphere covered in year-round ice sheets. The ocean levels were 120 meters lower than today, and the global average temperature was roughly 5 to 7 degrees lower than it was right before humans' industrial revolution. From what we know from the ice cores and thousands of measurements, the carbon dioxide level was 180 parts per million while this was happening, which is around the usual minimum for ice ages, and close to the minimum we've seen in our records. Then the usual cycle kicked in and CO2 levels rose to 260 parts per million over roughly 8,000 years, which is close to the maximum we can see of 300 and kicks off the period we call the Holocene. Then, human industrial revolution comes along and CO2 levels skyrocket to 412 parts per million, which puts us more than an ice age difference worth of CO2 above the Holocene, all within around 200 years. Most recently, that's been increasing almost 180 times faster than the Earth would ever do naturally. So yes, by any reasonable definition, you could say that we are definitely having a very big impact on the whole planet, or at least the greenhouse gas concentration. But we still have to answer the only question that matters. Do we know for sure that our greenhouse gases are driving up the temperature? Well, going back to those ice ages briefly, we know from our ancient measurements that even though CO2 would usually only account for 20% of the greenhouse effect, it can heavily influence global temperature, and vice versa. We know this because when we look back at the changes in temperature and CO2 levels across 800,000 years, we can see that they follow the same shaped pattern, and that temperature fluctuates in the range of roughly 6 degrees Celsius up and down. Right here, it's important to note that when we take measurements for temperature, we have to do it all over the world with a bunch of different strategies, because while CO2 is naturally average around the globe, temperature isn't, so we need an average. But looking at this graph, it appears that sometimes temperature changes first and sometimes CO2 changes first, which doesn't seem to make sense at first, but we have an explanation. You see, we actually know that the source of this fluctuation is due to changes in the Earth's orbit, or what's called Milankovitch cycles, which cause the Earth to be a bit further or closer to the Sun every 100,000 years. But from our calculations, we can't see how this change alone would create such big differences in the Earth's temperature. What does explain the difference is addressed in a study released by Associate Professor Jeremy Shakun and a few friends in 2012. Their study showed us something which makes much more sense when we run the calculations. When Earth exits ice ages, the orbit changes to let the Sun hit the North Pole more intensely and melt massive amounts of ice. This floods the oceans with warm, fresh water, and when the oceans on average become a bit warmer, they release a bit of CO2. So a cycle of heating and emissions begins and temperature rises, until the Earth's orbit changes again to give the North Pole a break. So the Sun is enough to heat the Earth a little bit, but carbon dioxide amplifies that heating effect a whole lot, and that's how we can explain such big differences in global temperature. Which makes sense because it reinforces the theoretical principles we know about greenhouse gases. Now we can look at what's happened in the past 2,000 years. Tens of thousands of temperature measurements and historical records across the planet show that the average temperature has increased by around 1.1 degrees since the Industrial Revolution, with most recent increases being 15 times faster than what we've seen when the Earth comes out of ice ages. And we can reasonably expect it to get a whole lot hotter and faster because our emissions have a delayed effect. From what we know of the theory, the CO2 molecules we pump out take around 10 years to come into full heating effect. Now, this may be enough to convince you that human-produced greenhouse gases are causing climate change, yet you may still have doubts that this could be a coincidence or correlation rather than causation. And that's okay, because scientists have thought that too. So what scientists did was they made a list of all things that we know of that could possibly explain the rise of temperature by natural causes. What if the Milankovitch cycles are doing something unexpected? What if the sun is getting hotter? What if volcanoes are doing more than we are? What if it's the ozone layer, or water vapor, or the Earth's core? What if humans are producing more CO2 just by breathing and there's no point doing anything about it? Well, actually, just on that last one, we don't count breathing as contributing to warming because all that CO2 can be traced back through our food to a plant which sucks CO2 out of the air not too long ago, so the effect is zero. As for the rest, the quick answer is that we've measured them all and none of them are increasing, or even changing very much, especially over the recent 100 to 200 years. You can read up on them more if you're still skeptical, but the most recent IPCC report shows a graph of what we think the temperature should have done since 1850 according to all of the natural sources we've measured. It includes a margin of error where we can be 95% confident that the truth lies somewhere in between. Then, when we think about everything that humans have done, we can do the same calculations of what we think should have happened with all of our cutting edge technology and add another margin of 95% confidence. Notice that since 2020, these margins haven't overlapped. But then we can overlay the actual temperature measurements, and there you have it. For the most part, it lines up very well with the predictions of human effect. This is the final piece of evidence, in the fastest yet most thorough explanation we could give, to say that humans are definitely driving up the Earth's temperature. But now that you know we're definitely causing the temperature increase, it's time to answer a much more critical yet underrated question. What should we expect to happen with climate change? And is it definitely a bad thing?